we are going to see an example for relations. The given sum is prove that the relation R, the set of all integers defined as relation R equal to the set of all ordered pairs x comma y such that x minus y is an integer, is an equivalence relation. You have to prove this is an equivalence relation. For an equivalence relation, we need three relations: reflexive, symmetric and transitive. Before that, when a relation is talked about, there must be a set and a relation. Two things are needed. As we said in the previous class, here the set is z, all for integers. Z equal to, we know that z equal to dot 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 minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, etc. up to plus infinity. These are the set of numbers form set of integers z. The relation is given as an ordered pair x comma y is such that x minus y is an integer for all x comma y belongs to z. For an equivalence relation, first we need to prove reflexive relation. Before that, given the set z of all integers, z of all integers, negative integers, 0 and all positive integers. The relation R is given as R equal to set of all x comma y, x minus y is an integer. We have to prove this. First one is reflexive property. For reflexive property, we need one element in the set, and for symmetric property, we need two elements in the set, and for transitive property, we need three elements in the set. Now, for reflexive property, we have to choose one element. Let a number A belongs to Z, an element from the set. Now, the relation A related to A equal to, that is A comma A is, according to the formula, x comma y means x minus y, where A comma A means A minus A. The answer is 0. 0 is an integer, belongs to Z. 0 belongs to Z. Therefore, A comma A belongs to R. Simply, the element is taken from the set. The relation ordered pair is taken from R. Now we have taken one element A. We are applying the relation A. That means two elements in the same bracket. Then applying the formula. In this sum, this is the formula. Therefore, A minus A equal to 0. The resulting number is also an integer. Therefore, this set A comma A ordered pair belongs to R. Therefore, reflexive property is true. Reflexive property is true. Now, symmetric property. Symmetric property. For symmetric property, we need two elements from the set, and we are going to apply this relation, this formula. Let A comma B belongs to Z. Single element எடுக்கும்போது செட்ல எடுக்கிறோம். Single element எடுக்கும்போது செட்ல bracketல போட்டாச்சுன்னா that is in R. இப்போ ரெண்டு element belong to the set. We are going to apply the formula. A comma B equal to, according to the formula, A minus B is an integer. If you put B comma A, B minus A is also an integer. To prove this, A comma B, A equal to, let A equal to 5, B equal to 17. Now apply this side, A minus B. A minus B equal to 5 minus 17, it is equal to minus 2. This answer belongs to the set. If we change the order, if we put B minus A, then it is 17 minus 5, it is plus 2. This is also an element of the set Z. A minus B is an integer. In turn, if you turn this, B minus A is also an integer. Only the sign differs. Both the number belong to the set Z. Therefore, A comma B or A related to B implies B related to A. Therefore, the relation R is symmetric. We need to taken two elements and prove this result. For transitive property, we need three elements A, B, C belong to Z. Here, single element we proved. For double element, if A minus B in an integer, the reverse order B minus A must also be an integer. We have proved this one. Therefore, A related to B implies both related, B related to A. This is the property for symmetric. This is satisfied. Therefore, R is symmetric. Now, for this one, using A comma B belongs to R. Then B comma C also belongs to R. Then we have to prove AB, BC, therefore AC, therefore A comma C must also belong to R. You have to prove this one. For this property, for A comma R, A related to B equal to A minus B is an integer. For this bracket, B related to C, that is B minus C is also an integer. Therefore, if we add these two, A minus B plus B minus C, cancel these two. Therefore, A minus C is also an integer. A related to B, A minus B, B related to C, B minus C. Then, if we add these two, A minus C, A minus C also is an integer. Therefore, the property, transitive property is true. Transitive property is true. First, we assume this one granted. Then, if we reverse this is also an integer. We proved here. We assumed A comma B belongs to R. That is A related to B, and B comma C belongs to R. That means B. This ordered pair BC also. B minus C is also an integer. Then, if you use these two, A minus C must be an integer. For this one, to prove A minus C, take the two results and add. We get minus B plus B cancelled, therefore A minus C. Using these two, we get A minus C. Using these two, we get AC. Therefore, A minus is also an integer. Therefore, the property, therefore, we have to write A comma C also belong to R. Therefore, transitive property is true. Since all the three properties are satisfied, therefore, the relation, given relation R is an equivalence relation. Just recall, given a set Z of integers, R is the relation. R is defined as, if you take the ordered pair x comma y, then x minus y is an integer. For all x comma y belongs to Z. இல்லை வர x y எழுத்து எல்லாமே இசட்ல இருக்கும், இந்த இசட்ல இருக்கும். அதை பிராக்கெட்டில் போடும்போது இந்த ஃபார்முலா அப்ளை பண்ணிடும். Now, அது what you have given, this carries half mark or 1 mark. In fact, it is a 5 mark question. What is the property? Single element. Symmetric property, 2 elements. Transitive property, 3 elements. The A comma A, same bracket. Here A comma B implies B comma A is also. A comma B is true, B comma C is true. Therefore, A comma C is also true. That is the third property. This is also true. Therefore, this is an equivalence relation that we have proved. This is an important question. Just revise this, and if you have any doubts regarding this, you can ask in the comment. Kindly subscribe RSR Maths channel and like it, share it. We will take the next example in the next video. Thank you.